Oh, okay. So I'm the host today. So first, I will briefly introduce this workshop. So first, welcome to the 2025 online COS workshop. First, as one of the organizer, so I would like to thank Professor Romani and Professor Yu for their suggestion regarding this online workshop. I would also like to thank all the speakers for accepting our invitations and for sharing their recent progress here. So this online workshop will be held over the coming 3 days and will feature 22 talks in the fields of geometric analysis and spin geometry. So we plan to record all the talks with the speaker's permission and upload them online for the future communication. Our technician is Xin Yu because he provides the Zoom link. Hopefully, as we discussed with Somali, we can continue hold this workshop every summer in the future and create the virtual communication opportunity for us. Okay, so this is my brief introduction. So next, I will introduce our first speaker, Milan. He is from Texas A&M. He is still a PhD candidate there. His title is a scalar-mean curvature extremality result for manifolds with iterated asymptotic canonical singularity. Okay, so Milan, so you can get started.
Okay, so thank you for inviting me. So I guess as the title says, I'll be talking about a recent result regarding the scalar mean curvature extremality or manifolds with singularities. So in particular, these manifolds have iterated asymptotically conical singularities. Okay, so here's the outline for my talk. So I'll first give some background and history for what leads up to our result. Then I'll state our theorem and also give the definitions needed to actually state the theorem. After that, I'll give a sketch of the proof for the theorem. And then I'll also give some additional applications of our methods. Okay, so starting with the history. So I guess from the 1960s to the 1980s, we had a lot of fundamental results on scalar curvature. So Lesch-Nerowitz proved his Lesch-Nerowitz formula and gave a topological obstruction to the existence of metrics with positive scalar curvature. In the 80s, Shane Yao and Witten gave two different proofs of the positive mass theorem, and Shane Yao and Gromov-Lawson around the same time showed that the torus doesn't have a metric with positive scalar curvature. Okay, so these results were kind of more qualitative, so they dealt with questions regarding existence. Okay, so then in the 90s, there's a shift towards more quantitative questions. So in 1996, Leroux proved that the sphere is scalar curvature extremal. Okay, so that means if you start with the standard metric on the sphere, you can't increase the scalar curvature and distances at the same time. This was generalized by Goat and Simmelman to spin manifolds with non-negative curvature operator. And then in a paper of John Lott in 2020, this was extended to spin manifolds with boundary, except now instead of having a scalar curvature comparison, you have a scalar curvature comparison and a mean curvature comparison. Okay, so that's kind of what's been going on since the 90s. Okay, so recently people have been asking these scalar curvature questions on singular objects. So in a 2021 paper by Wang, Zhi, and Yu, they study the Dirac operator of polyhedral manifolds. And using that, they're able to prove an extremality result for polyhedral manifolds. And in this case, they assume a comparison condition on scalar curvature, mean curvature, and dihedral angles. Last year, there was a paper by Dai, Sun, and Wang where they proved the positive mass theorem for manifolds with isolated conical singularities. And very recently, there was a paper by Sacchini, Hank, Schick, and Schonliner where they study the index theory of Dirac operators on manifolds with isolated conical singularities. Okay, so I guess these singular objects have been seeing activity recently. Okay, so here's the theorem that we prove. So I'll state the theorem and then I'll actually give the definitions. Okay, so the setup is that we have a compact spin manifold with iterated asymptotically conical singularities, and we have a smooth boundary dm. Okay, so we suppose that the links of the singularities of M have dimension at least 2, and we assume that the curvature operator associated to this metric G is non-negative, and the second fundamental form associated to G along the boundary is also non-negative. Okay, so we prove that if you take another metric G hat, which is asymptotically conical, and it satisfies the following 4 conditions. So first, we assume that G hat restricted to the boundary is equal to G restricted to the boundary, or we assume that the Euler characteristic of the boundary is non-zero. So that's the first condition. Second condition is metric domination. So we assume that the metric G hat dominates G. Okay, third assumption is scalar curvature domination. So we assume that the scalar curvature of G hat dominates the scalar curvature of G. And lastly, we assume mean curvature domination. So the mean curvature with respect to the metric G hat dominates the mean curvature with respect to G. Okay, so if the following 4 conditions hold, then we deduce that actually the scalar curvatures coincide and the mean curvatures coincide. Okay, so the part that I need to define for you is what's in red. Okay, so that's what I'll do next. Okay, so the actual definition for manifolds with iterated asymptotically conical singularities is a little lengthy. So instead of giving you the precise definition, I'll just give you a picture. Okay, so when we talk about manifolds with IACS, it's actually a hierarchy of manifolds. So you have C1 manifolds, C2 manifolds, and so on. And the higher this CK index is, the more singular the manifold is. Okay, so starting with C1 manifolds, here's the picture. So we take some topological space M, and we assume it has some distinguished subset. Okay, so we refer to the distinguished subset as the C1 singularities. And then away from the C1 singularities, we assume M is just a smooth manifold. And then at the C1 singularity, if you have a given C1 singularity, we assume that locally the manifold just topologically decomposes as a direct product of a base times a cone. And in this case, the link is just a smooth manifold. Okay, so at the singularity, it's just topologically a product. Okay, and then we also assume that we have a metric on this manifold such that around the singularities, the metric takes the following form. Okay, so in this trivialization, it looks like a family of cones parametrized over the base plus some error terms. Okay, so that's kind of the picture for what C1 manifolds look like. Okay, and once you have C1 manifolds, you can define the C2 manifolds. Okay, so for the C2 manifolds, the difference is that now we allow the links themselves to have singularities. Okay, so again, we start with a topological space M. Now we have a distinguished subset of C2 singularities. And around each C2 singularity, we assume that locally it just looks like a base times a cone. And in this case, this link L is going to be a C1 manifold. Okay, so the link now has singularities. And then we also assume that we have a metric on this space such that around the singularities, again, it's just going to be a family of cones over the base plus some error terms. Okay. So that's kind of the intuitive picture for what C2 manifolds look like. Okay, and so using this, we can define the notion of a CK manifold for all K by induction. And then we say M is a manifold with iterated asymptotically conical singularities if it's a CK manifold for some K. And the metric G associated to M is said to be asymptotically conical. Okay, so when we talk about manifolds with IACS, it's a space M and a metric G. So any questions on the kind of this picture? No? Okay, so next I'll just state some basic facts that hold for manifolds with IACS. Okay, so the first fact is that if you have a manifold with IACS such that the links of this manifold have dimension at least 2, if you define this function dc, it's the distance from a point to the closest singular point. If you look at 1 over that distance function, multiplication by this function is a bounded operator from h1 to L2. Okay, so that's kind of the first fact. And then the second fact is that, again, if you have a manifold with IACS and the links have dimension at least 2, then the inclusion of h1 into L2 is compact. Okay, so I'm just going to assume these facts. They're not too difficult to prove. You do it by induction, and it essentially reduces to applying integration by parts in Cauchy-Schwarz. Okay, so I'll assume these two facts, and using these two facts, I'll prove the theorem. Okay, so the proof of the theorem decomposes into 2 steps. So for step 1, we're going to prove the self-adjointness and Fredholmness of some operator dB. And for step 2, we're actually going to prove extremality. Okay, so let's start with step 1. Okay, so we need to prove self-adjointness and Fredholmness of dB. Okay, so before proving that, I actually need to tell you what is this operator dB. Okay, so here's how we construct dB. So we start by defining this vector bundle V. It's going to be 2 copies of the tangent space of M. And in the first component, we have the metric G hat. And in the second component, we have the metric G. Okay, so then now we consider the spinor bundle associated to V. So this is SV. We'll let D denote the Dirac operator on the spinor bundle. Because we have 2 copies of M, we usually call it the twisted Dirac operator. And we're not going to study D itself. Instead, we're going to study the restriction of D to a subspace. Okay, so we'll denote this restriction by dB. And dB is just the restriction of the Dirac operator to the smooth, compactly supported sections satisfying a particular boundary condition. Okay, so this is the boundary condition that we call B. Okay, so it's square root -1, Clifford multiplication of the inner unit normal from the first metric, composed with Clifford multiplication of the inner unit normal from the second metric. And then we assume that if we apply that to sigma, it's equal to negative sigma. Okay, so sigma satisfies the boundary condition B if this equality holds along the boundary. Okay, so the reason why we want to restrict to this subspace is because on this subdomain, dB is symmetric. Okay. Okay, so once we know dB is symmetric, we want to show that this operator is self-adjoint. So we want to show that the maximal domain coincides with the minimal domain. Okay, so in order to prove self-adjointness, first observation is that it's enough to prove self-adjointness locally. So this follows from the fact that if you take a smooth function in the maximal domain, if you take a section in the maximal domain and you multiply by a smooth function, it's still in the maximal domain. So applying a partition of unity argument, you can localize your problem. Okay, so we prove self-adjointness locally, and self-adjointness away from the singularity is just standard elliptic operator theory. So that means when we think about self-adjointness, we only need to worry about what happens in a neighborhood of a singular point. Okay, so in order to prove self-adjointness, we're going to localize at the singular points. Okay, so to prove self-adjointness at the singular points, we'll do it in steps. So first, we're going to think about the simplest case possible. So the simplest case possible is when you have an isolated C1 singularity with no error terms. So if you localize at this isolated C1 singularity, you essentially get the following model case. So your manifold is just the cone of some smooth, compact Riemannian manifold L, and then the metrics G hat and G are just cone metrics. Okay, so this is the model case right here. Okay, so in order to prove it in this model case, we'll start by identifying the L2 sections of the spinor bundle of V with this other space. So it's kind of like a cylinder. So it's L2 of this space. And the identification between these two spaces is essentially you take a section at r is equal to 1, you parallel translate it in the radial direction, you multiply by some sort of rescaling, and that will give you a unitary operator to this space L2 of SV. Okay, so there is a canonical identification between the two spaces. I'm not going to write it out, but the point is that under this identification, the Dirac operator D takes the following form. So you have this kind of radial derivative plus 1 over r, and then you have this operator p on the anti-diagonal. Okay, so here p is the negative of a modified Dirac operator. So the definition for this modified Dirac operator d partial 0 is given as follows. So d partial 0 is going to be the sum from 1 to n minus 1. So it's going to be Clifford multiplication by the radial direction composed with Clifford multiplication in the link direction applied to the derivative, this nabla partial 0 applied to sigma. Okay, so here this nabla partial 0, it's not the usual spinor connection, it's a modified version of it. So it's the spinor connection minus the radial contribution. Okay, so essentially the idea is that we're essentially just removing the radial contribution from the first component. Okay, so this is what the model case is going to look like. Okay, so operators of this form have already been studied in the literature. So there's a paper of Bruning and Sealing where they give a condition for when this operator D is going to be self-adjoint. So it turns out that it's self-adjoint if and only if you have a spectral gap for P at 1/2. So what that means is that the eigenvalues of P are outside the interval from -1/2 to 1/2. So if we can prove that P has this spectral gap, that will imply self-adjointness. Okay, so in order to prove self-adjointness, we need to use our geometric assumptions. So we'll start by applying the Eliashine-Arrowitch formula to D partial 0. So maybe I should have just written P here. So if we look at P squared, the Eliashine-Arrowitch formula tells you that it's going to look like this. So you'll have a non-negative Laplacian term, then you'll have the scalar curvature of this link metric G hat L divided by 4, plus a curvature endomorphism coming from the twisting. So one of the estimates proved in this paper of Gott and Simmelman that I mentioned at the beginning says that this extra endomorphism term that we get is bounded below by the negative scalar curvature of G evaluated at r is equal to 1 divided by 4. So if you look at the scalar curvature formula for a cone and you plug in r is equal to 1, this is what you're going to get. Okay, so if we go back and we plug that into our Eliashine-Arrowitch formula, this gives us a lower bound for p squared. So we see p squared is bounded below by this non-negative operator plus this scalar curvature term minus this other scalar curvature term. Yeah, so this right here is a typo. I should have written p squared. Okay, so that's the first observation we make. The second observation is that now we are going to apply our geometric hypothesis. So the geometric hypothesis says that the scalar curvature of G hat is bounded below by the scalar curvature of G. If you write out what that means in terms of the scalar curvature formulas for a cone, it tells you that this left-hand side is bounded below by this right-hand side. And so now if you cancel out r squared, if you cancel out the common factor of r squared, and you cancel out this common factor of n, what this inequality implies, it implies that actually you have scalar curvature comparison on the links. Okay, so the scalar curvature of this G hat L metric is dominates the scalar curvature of GL. Okay, so if we go back and we plug that into our estimate for p squared, this is what we had. This is what we had in the last slide. And we just showed that this scalar curvature term dominates this scalar curvature term. So that means we can erase them. So it tells us that p squared is actually bounded below by this non-negative operator plus this factor of n. Okay, so if p squared is bounded below by this, then that tells us that the modulus of p is bounded below by this square root of n factor divided by 2. Okay, so as long as the dimension of the links is at least 2, this number is greater than or equal to 1/2. And so that will allow us to apply the result of Bruning and Seeley. So any questions on that?
So,
No?
I have a question. So your link is just a hypersurface in this case, right? Just one singularity in this case, right? By your assumption, your simplest case.
Yeah, so we're only looking at C1 singularities, so the link is a smooth compact manifold.
Oh, okay, I got it.
Yeah. So this is the simplest case, is just no singularities on the link. Any other questions?
Do
Okay.
you have arrow terms? You don't exactly.
So remember, I'm only doing the simplest case possible. So right now I'm just assuming isolated singularity with no error. So that's going to be the next case, how to deal with the error. Okay, any other questions? Okay, so the next case that we're going to consider is the general case for C1 manifolds. So we're going to consider non-isolated C1 singularities with error terms. Okay, so in general, if you localize at a C1 singular point, you're going to have a base space product with a cone. And then your metric G hat, it's going to be a family of cone metrics plus some error terms. And G is also going to be a family of cone metrics plus some error terms. So this is what the general case will look like. And so the idea will be to reduce to this model case that we just considered. So this is how we're going to do it. So we're going to start by defining two new metrics, G hat prime and G prime. And essentially all we do is we just freeze what happens at this singular point B0. Okay, so this is the singular point that we're localizing at. And we just freeze the metrics at this point, and we remove the error terms. Okay, so we define these two metrics, G hat prime and G prime. And so once we have these two metrics, we can define a new twisted Dirac operator. Okay, so essentially what's going to happen is we're going to compare the original twisted Dirac operator with this model case, with this new Dirac operator coming from G hat prime and G prime. Okay, so let me set up the notation in order to do that. So dv prime will denote the twisted Dirac operator on SV prime. And here v prime, it's again two copies of m. But in the first component, we have this modified metric G hat prime. And in the second component, we have the modified metric G prime. Okay, so this is the new Dirac operator that we want to compare to. And in order to keep the notation clear, I'll decorate the original twisted Dirac operator that we started with a v. Okay, so dv is the original operator. We want to show this as self-adjoint. And dv prime is the new operator that we want to compare with. Okay, so how do we compare dv prime and dv? Well, there's a result from this 1992 French paper. They give a construction on how to get a unitary between SV prime and SV. And their construction also gives a formula for what the Dirac operator is going to look like under conjugation. Okay, so applying their result, if you look at the difference between dv and dv prime, the difference between the two operators will have order 1 over r times this function L of b, or order little o of 1 over r. Okay, so the error between dv and dv prime has error terms which look like this. Okay, so here L of b is just the distance between b and b naught along the base. Okay, so what this tells us is that if we're looking at the error between dv and dv prime, by shrinking the base direction to be very small, we can make this coefficient small. And remember also that one of the results was that multiplication by 1 over r is bounded. So if we have something small times something bounded, then this whole thing is going to be small. And if we shrink the neighborhood in the radial direction, we'll make this little o of 1 over r term small. Okay, so to be precise, what we can show is that if we shrink the neighborhood around the singular point b naught, if you look at the difference between dv and dv prime, applied to some section sigma, if you look at the L2 norm squared of this difference right here, you can bound that above by a constant multiple of a times the L2 norm squared of sigma plus b times the L2 norm squared of dv prime applied to sigma. And by shrinking the neighborhood small enough, we can guarantee that b is strictly smaller than 1. Okay, so if you recognize this inequality, this is the inequality that you need in order to apply the Cato-Rella perturbation theorem. Okay, so the Cato-Rella perturbation theorem says that if this inequality holds, then the self-adjointness of dv will follow from the self-adjointness of dv prime. Okay, so that's how we reduce self-adjointness to the model case. So here dv prime is just a flat space times the model case. So any questions on that?
Can you go back to previous page? I forgot the v prime.
So
No,
we're just, yeah. So
yeah.
v prime is just 2 copies of m, but now with the new metrics g hat prime and g prime.
Okay, okay. Same space v.
Yeah, same space, just new
Different
metric.
metric.
Yeah.
Okay.
And that's why we get different Dirac operators.
So I have a question. No, go back. So how, you didn't construct the, no, is it trivial to construct your new metric? Or you didn't do that? Here.
So, I mean, so this is the new metric right here. We're
Yeah.
just fixing what happens at b naught. So you just fix what happens at b naught and you spread it out everywhere.
Okay.
Yeah, so the idea is that I want to reduce it to the model case where there's no variation of the cone operator and there are no error terms. So we just fix it. We fix b naught and remove the error terms.
Oh, okay, okay.
So any other questions? Okay, so yeah, so once you reduce to the model case, that's essentially how you show self-adjointness for C1 manifolds. And remember the other basic fact I assumed is that H1 compactly embeds into L2. So if you have self-adjointness and you know that the domain is compact, then that allows you to get a compact resolvent, and that implies Fredholmness. Okay, so that's kind of the sketch for the proof of self-adjointness and Fredholmness in the C1 case. Okay, so once you prove the C1 case, then you prove the C2 case. So you prove the C2 case, the case of C2 manifolds, after you prove the case of C1 manifolds. So the strategy is the same. You'd first consider the model case where you have an isolated C2 singularity. Once you prove it for the model case where you have an isolated C2 singularity, you'd prove it for the case where you have a non-isolated C2 singularity and error terms by reducing it to the model case. And then you continue that process by induction. Okay, so that's as far as I'll go in terms of proving self-adjointness and Fredholmness. So any questions on that? Okay, so if there are no questions, then now we're ready to get to step 2 of our proof. Okay, so for step 2, this is where we actually prove extremality. So the index of these cone operators, of these Dirac operators on singular spaces, in general, the index is not computable via a local formula. In general, you'll have some eta invariance okay, that aren't locally computable. And so we don't try to compute the index. Instead, we just directly look at the kernel of this operator dB. Okay, so we'll distinguish between two cases. So for case one, we assume that the kernel of dB is non-zero. Okay, so if the kernel of dB is non-zero, then we can take a non-zero section in the kernel. And by applying Stokes' theorem and the Lesch-Nerowitz formula, we get the following lower bound on the L2 norm squared of the Dirac operator applied to sigma. Okay, so this term is going to be bounded by the integral of this derivative plus the integral of the difference of the scalar curvatures plus the integral of over the boundary of the difference of the mean curvatures. Okay, so this is what you get on the right-hand side. But we also assume that sigma is in the kernel. So on the left-hand side, you just get 0. Okay, so now if we apply our geometric hypotheses, remember we assume that the scalar curvature of g hat dominates the scalar curvature of g, and the mean curvature of g hat dominates the mean curvature of g. So that means that every term on the right-hand side is non-negative. So you have a sum of 3 non-negative terms is equal to 0, and that means that each individual term must be 0. Okay, so this integral must be 0, this integral must be 0, and this integral must be 0. And so using that, we can conclude that sigma is parallel, that the scalar curvatures coincide, and that the mean curvatures coincide. Okay, so this is case one. So any questions on that? Okay, so for case two, this is the kind of the more difficult case. So in case two, we have that the kernel of dB is equal to 0. Okay, so in order to handle this case, we're going to have to do a little more work. Okay, so in general, if you have a smooth section sigma, and suppose that when you restrict it to the boundary, it decomposes into sigma 1 plus sigma 2, where a sigma 1 satisfies the boundary condition B, and sigma 2 satisfies the boundary condition B perp. So in general, if you have a smooth section sigma of this form, then when you apply Stokes' theorem and the Lesch-Nerowitz formula, this is the lower bound that you get on the Dirac operator. So you'll have the L2 norm squared of the Dirac operator applied to sigma is bounded below by the derivative term, the scalar curvature term, and the mean curvature term. But in general, you're going to have this extra integral right here. So it's the integral over the boundary of the boundary Dirac operator applied to sigma 2, inner product with sigma 1. Okay, so in general, this is what you'll get. So if sigma satisfies the boundary condition B, this term vanishes. So that's why it didn't show up in the last case. And so essentially, what we want to do is we want to find a section sigma, which is a harmonic spinor, and such that this integral vanishes. Okay, so if we can find a harmonic spinor which makes this integral vanish, then the same argument from case one will imply extremality. Okay, so how can we find this section sigma? Okay, so let's see. So in order to find a section sigma satisfying these two properties, we can solve the following differential equation. So we want to find a section sigma such that the Dirac operator applied to sigma is equal to 0 on M. And we want that this section sigma to also have the property that if you look at the boundary Dirac operator applied to sigma 2, that's going to be equal to 0. Okay, so if we can find a section sigma satisfying these two equations, then the integral is going to vanish because this term is just 0 and it's a harmonic spinor. So we can apply the same argument from case 1. Okay, so we need to solve this equation. Okay, so how can we solve this equation? So if you remember the geometric hypothesis, there were two conditions. The first condition is where the two metrics coincide on the boundary. So where we assume g hat coincides with g along the boundary. And the second condition is where we assume that the Euler characteristic along the boundary is non-zero. Okay, so in the first condition, where the metrics coincide along the boundary, if you look at SV, since the metrics coincide along the boundary, if you restrict the spinor bundle to the boundary, you just get the Clifford algebra. Okay, so since the spinor bundle restricted to the boundary is the Clifford algebra, you can just take sigma 2 to be the inner unit normal. So if you take sigma 2 to be the inner unit normal, it will satisfy the boundary condition B perp. And also, if you apply the boundary Dirac operator to sigma 2, you'll get 0. Okay, so this is what sigma 2 will be in the first case. In the second case, where you assume that the Euler characteristic of the boundary is non-zero, we can construct this section sigma 2 using the Atiyah-Singer index theorem. Okay, so the classical Atiyah-Singer index theorem applied to this boundary Dirac operator will guarantee that there's a non-zero element in the kernel. Okay, so that's how you find sigma 2. So how do you go from sigma 2 to sigma? Okay, so let's see. So in order to construct sigma from sigma 2, we extend sigma 2 to the interior. Okay, so sigma 2 right now is only defined along the boundary, and we just do a smooth extension to the interior, call that psi 2. So any smooth extension will work. Okay, just choose some smooth extension. Okay, so once we have this smooth extension, we recall that in this case, we assume that the kernel of dB is equal to 0. Okay, if the kernel is equal to 0, well, we have a self-adjoint Fredholm operator. That means that dB is actually invertible. And so using the invertibility of dB, we can find a section psi 1 such that the following differential equation is satisfied. So dB applied to psi 1 is equal to negative d applied to psi 2. So now we define sigma to be psi 1 plus psi 2. This equation guarantees that sigma is a harmonic spinor. Okay, so that satisfies this first equation right here. And if you look at sigma restricted to the boundary, psi 1 satisfies the boundary condition B by construction, and psi 2 satisfies the boundary condition B by satisfies the boundary condition B perp by construction. And also by construction, if we look at D partial partial applied to psi 2 along the boundary, it's going to be 0. Okay, so if we take sigma to be this, that will solve the differential equation, and then we can reduce to case 1. Okay, so that proves extremality. Any questions on that?
So I already forget the definition of dB.
So remember, dB is the twisted Dirac operator, where it's restricted to a subdomain where the sections satisfy a boundary condition B.
Okay. But what's no? So for the equation, not the boundary condition, what's the relation between dB and the D? I just forget it.
So dB is the restriction of D to a subdomain.
Just a boundary, different boundary, the same operator, dB, right?
So yeah, so D has no restriction on the boundary. dB has the restriction on the boundary. Same
okay,
operator.
I got it. Thank you.
Yeah. Okay, any other questions? Okay, so that ends the proof of extremality. And then just as a last slide, I'll kind of just tell you some additional applications for where we use our framework to reprove some standard theorems in the smooth case in this singular case. So as a first application, we kind of have a rigidity theorem for non-negative scalar curvature fill-ins. So here's the setup. So we take a compact manifold M with iterated asymptotically conical singularities and smooth boundary. And we assume that the lengths of M have dimension at least 2. Okay. And so now we suppose that the boundary embeds into Rn as a closed convex hypersurface. Okay, so when we view the boundary as a subset of Rn, we'll denote it by sigma. Okay, so sigma as a subset of Rn has the induced metric G sigma. So now on the boundary you have two metrics. You have the one induced from M and the one induced from Rn. So now our theorem states the following. So if the metric on the boundary induced from M coincides with the metric on the boundary induced from Rn, if they're equal, or if the dimension of M is odd and we have the scalar curvature domination. So this metric induced from M dominates the metric induced from Rn. That's the first condition. Second condition is that we assume M has non-negative scalar curvature. And the third condition, we assume that the mean curvature of the boundary as a subset of M dominates the mean curvature of the boundary as a subset of Rn. If these three conditions hold, then we deduce that G is flat. Okay, so that's kind of the first application. And then a second application is that we prove the positive mass theorem for our singular manifolds. So if we have an AF manifold with iterated asymptotically conical singularities, if the links of this manifold have dimension at least 2 and the scalar curvature of M is non-negative, then the ADM mass is non-negative. And if the ADM mass is 0, then G is flat. Okay, so that's the positive mass theorem for this singular case. Okay, so those are some additional theorems that we're able to prove using this framework. And so, yeah, that's all I had. So any questions on that?
Right, so I have a quick question.
Yep.
Yeah, so for the positive mass theorem, do you have any spin restriction for the manifold or dimension restriction on that?
You're right. So I should say spin AF manifold. Yeah, thank you.
Yeah, thanks.
So I have another question, Mina. So at the beginning, you mentioned their result, compared to yours result recently, what's the difference? Because I haven't read their paper. Can you tell us?
So they dealt with isolated singularities, and we deal with
yeah. But this I have one question first. In which part you essentially use the isolated ACS? Where you use it, in the part of dual reduction, the metric part. Where do you essentially use this assumption?
So I guess, are you asking how do we reduce to the simple case?
Yeah. Did you essentially use this assumption here? No.
Yeah. So I guess you use this assumption for what?
Use assumption to you use this special isolated isolated singularity to prove this theorem, right? See in this part, not this part. Of course, this is the simplest case, automatically satisfies the isolated. How about the complete case? You do the reduction part, right?
Yeah, so that's this second part right here.
Yeah. No, here. This part you essentially use the singularity or something here.
Yeah. So I mean, this is the isolated singularity right here. So let's fix it. And now we have a flat metric because we just fixed the metric on the base.
Yeah.
So essentially, once we reduce it to this case, it's just a flat space times the model case. So that's how we reduce it to the model case.
Oh, okay. Yeah, that's any other questions? We still have time. Okay.
Can I ask a question about asymptotically flat positive mass theorem? Also, what you use is twisted or proof of Witten. What you use is
sorry, I didn't hear it. What was the question?
regular inner bundle.
It's either my internet connection or your internet connection. It keeps cutting out. I didn't hear the question.
I cannot hear it all. Okay. I think it's Xiaoxiang's internet issue.
Okay.
Oh, I will type. Someone else can ask questions.
Now it's clear. Okay.
Oh, okay. So what I'm asking is that the original proof of Witten he uses one component of the spinor bundle. Here your positive mass theorem, do you use twisted spinor bundle?
No, we can use one component as well.
I
So
see.
the twisting is there because we need to compare two. In the first theorem, we have to compare two different metrics. In this case, it's only one metric, so we can also we can deal with one component.
Okay.
So Mina, I have another question. I haven't read your paper now. So
Yeah.
By my understanding, the first is Scalar-mean, right? Scalar-mean rigidity.
Yeah.
Right? In the paper, did you really write the details about the positive mass theorem, or just because the Scalar-mean is equivalent to it? I haven't read the paper.
Yeah, so it's in the paper. So the proofs of both statements are in the paper. I just didn't think I have
I mean the last one, the positive mass theorem. You have the details.
Yeah, the details are in the paper.
Oh, okay, I'll check it. So, any more questions? Okay, so since there is no more question, so let's end our first talk. Okay. Thank you, Mina. Yeah.